In the last lecture, we justified how NMR works from the perspective of a single spin. But if you've done any NMR spectroscopy before or interpreted spectra, you know it's a little bit more complicated than that. The spins can interact, and all those signals that we see aren't just single straight lines, but they're split into doublets, triplets, quartets, or even more complicated structures than that. So we're going to start being able to justify that using the quantum mechanics and the idea of quantum states that we now know. So we're going to have a look at what happens with two spins, and we're going to touch upon the idea of entanglement, not in a lot of detail, thankfully, and then we're going to look at energy levels for either degenerate or non-degenerate spins. Are the protons that we're looking at in the same chemical environment or not? Because how they couple together and how they interact will change, and it has a really interesting consequence which we explore in the final lecture. So let's recap spin again. We have two spin states. One we call spin up, we label it alpha. One spin down, we label it beta. And those have different energies that are proportional to the magnetic field we put it in. Put it into a big magnetic field, the energy difference between the two is a lot bigger. So how do we get a doublet? If we just have these two energy fields, we'd only ever see one spike on the NMR spectrum, not more than one. So we've got a transition between alpha and beta. If we put a second spin in there, the conventional story that you'll be told is that the other spin could be pointing up. And if it's pointing up, it kind of increases the magnetic field. So the field felt by this proton that we're measuring could be higher, in which case the energy splitting is ever so slightly bigger. But spins can point up or down. So in the other 50% of cases, that second spin is going to be the opposite direction. It works against the field, and therefore the energy difference is a bit smaller. So what we have is got an energy difference of that, an energy difference of that, two energies, two potential energies of photons that could cause a transition there, two spikes on the NMR spectrum. And the same thing happens to this proton as well. The same argument applies, so we end up with two doublets. The first one split into two, the second one split into two as well. So if we're looking at four signals in total, four different transitions, so two sets of doublets. So we need to be able to explain four different transitions when we're doing quantum mechanics. And we've got to be a little bit more detailed than just saying that, well, it feels the effect of the next one along. So what we're going to do is to combine spins. So we're going to take the spin of the first one, the spin of the second one, and add them together. And we're going to be able to describe these spins as a single state. So if the first one is pointing up and the second one is pointing up as well, we've got two states, alpha, alpha. If the first state is pointing down and the second one is pointing up, we've got beta alpha. And the same thing goes for the other way around. First spin is alpha, second spin is beta, or both can be pointing down, in which case we call it beta, beta. So we've got here a shorthand way of saying, well, we've talked dealing with one state. We're going to compress that down to just say it's psi alpha alpha, psi alpha beta, beta alpha, or psi sub beta beta there. So four possible sets of spin states. These spins are basically entangled together. The two protons are being described by the same wave function. That's the interesting part about how this works. We're describing more than one particle with the same function. That'll be familiar to you if you've done atomic spectroscopy and terms and states, because those terms and states and levels usually involve treating multiple electrons and multiple spins as one object and just describing it with a single term. Here we're describing different spins, two protons, with the same wave function. So how do we arrange these in terms of their energy? It's fairly simple to do for alpha alpha. Both spins are pointing up. They're with the magnetic field. We must get a lot of energy back here, so they're going to be the lowest energy state. Same with beta beta. Those are both against the field. It takes quite a bit of energy, so they must be the highest energy state. Great. What about the other two? One's pointing up, one's pointing down. The other one is pointing down then up. those must be, well, the same energy, aren't they? They're effectively the same state, but swapped around. Couple of problems here. Well, this, at most, gives us 3 transitions, one to the other, or jumping up from the alpha alpha to beta beta state. So that doesn't replicate the double doublet idea that we saw earlier, which requires 4 transitions. So why would these 2 in the middle be degenerate? Well, there's no reason they should be. If they're on a different part of the molecule, the fact that one is pointing up and the other is pointing down would be different. They'd have different energies. So there would be a split here. There would be no degeneracy between them. So that gives us a lot more transitions. We could go here to here to here to here to here to here. Okay, that's a lot more transitions than we're looking for. So let's look at a selection rule. The selection rule for the spins here says that we can only change one spin at a time. That's an angular momentum argument. A photon of light that comes in has a certain amount of angular momentum associated with it, so that can only change the angular momentum of the spins by a set amount. Specifically by 1. It can flip a spin up to down, but it can't flip 2 at the same time. So let's see what that can do. If we start down here, we've got alpha alpha, that can jump up to here. We split the second spin and we flip it down. We could also flip the first spin down and get to here. But we couldn't flip both spins at the same time and go alpha alpha to beta beta beta. That is forbidden. That can't work. But we could start on alpha beta and flip the first one so that it's pointing down again. That sends us up here. Or we can start on beta alpha, flip the second spin so that both are down and go there. And there we have 4 transitions that are allowed. We can't do a one in the middle because the alpha would have to swap to a beta and the beta would have to swap to the alpha. That's 2 flips. Not allowed. We can't do that. So we've only got 4 transitions of 4 slightly different sizes. There we go. This is a good sign. We're now explaining why we get 2 doublets when we look at 2 spins. So conventionally in NMR, we format this diagram like this. We actually split these 2 middle ones slightly along the x-axis. There's no particular reason for that. It just makes it look a little clearer. If we overlaid them like before, it gets quite messy. Here we can see 4 separate transitions. It also allows us to do transitions in the middle and draw them out. Those do sort of exist. They're called multiple quantum coherences. They're indirectly used in more complicated NMR experiments, so they can be sort of observed, but we're not going to consider them. We're assuming that those are spin forbidden. The energies associated with them cannot be directly detected through a simple spectroscopic, energy level thing. They are spin forbidden. So if we have a look at the size of these arrows and the way that those energy levels are offset by, well, we find 4 different energy levels, or 4 different amounts of energy here. 2 very similar looking ones, 2 very other similar looking ones, but they're still slightly different. And of course, that then shows up as 2 doublets. One much more further shifted because these are overall bigger, one shifted a bit less because it's smaller, and then a tiny difference between the 2 manifests as the doublet. So what we've managed to do is replicate the idea of 2 doublets from the idea of quantum states by treating them as if they are governed by the same wave function and the same state. We can order them by energy, find the transition between them, and get this spectrum out. So this diagram here really only applies if the protons are in a different chemical environment. So if we've got, let's just draw a molecule and we have, let's make it an ethane derivative. Those would be in the same chemical environment. But if we put chlorine there and iodine there, for instance, now they're in a different chemical environment. Those 2 protons can be distinguished. They would be described by this energy level diagram and we get 2 doublets out. So what if they're degenerate? So here we've got 2 identical spins. Let's say in just two hydrogens attached to each other, or H2, the H2 molecule. So we can do one pointing up, one pointing down, maybe one pointing up, one pointing up, one down, then up. We can do all four of those combinations as before and get this out. But there's no way of distinguishing the two in the middle there. And there is a bit of permutational symmetry involved here. It's related to the Pauli exclusion principle that says we can't have those as states. They're not actually valid. So we can't actually use this set of descriptions in those wave functions to describe the H2 molecule. That's not the spin states that we find when it's symmetrical. So if we have trouble with our existing wave functions, we normally just solve that by taking superpositions. These linear superpositions here are the actual spin states of H2. We've got one here where they're both pointing down. Okay, that's fine. We've got one here where they're both pointing up. That's fine. The two in the middle are combinations of our up-down and down-up states. That's really hard to visualize in this method. How do you actually add these together? Wouldn't that cancel out to nothing? How do you subtract them, for instance? And okay, fair enough. This makes a lot of sense when you consider the angular momentum of the spins, not necessarily when you visualize it like that. But nevertheless, these are the equations that govern it. So that is how we lay out four spin states for an H2 molecule. That's going to have some consequences in the final lecture when we talk parahydrogen. So two or more spins are going to be described by just one wave function. We're labeling that psi alpha alpha. Occasionally, if you want, I'll put it in for completeness. We'll occasionally put it in Dirac notation. We could do that next term if you're interested. Now, two spins lead to four energy levels, and then when we apply the selection rules, we get four transitions. If we've got four transitions, we get our doublet and our second doublet, which is what we see in the spectrum. It's a little bit more complicated if you want to do more than two particles, but we can replicate doublets, triplets, and so on. The more advanced series deal with that a little bit better than this energy level approach, but that's out of our scope for now. For now, we just are interested in what happens when we've got two spins, and we'll leave the complicated maths of 4, 10, 20 spins to the professionals.